This screencast is in place of lecture for September 27th in Math 102. Today I'm going to say a little bit more about Newton's method, go through an example, and talk about how best to choose your initial guess for Newton's method. Okay, so Newton's method is used for finding zeros of a function. So let's call the function we're finding zeros of f of x. There's a few different places where this method is often used. It can be applied when looking for critical points, because critical points are points at which the derivative of a function is equal to 0. So if we define f of x as g prime of x, then Newton's method will find, if we apply Newton's method to f of x, it'll find the zeros of f, which are the zeros of g prime, which is what we call critical points, potential mins and maxes or inflection points. We can also find intersections of functions. For example, two functions will cross when g of x is equal to h of x, and by rearranging that, we can define a function f of x that's g of x minus h of x, which will be 0 whenever g of x and h of x cross. And finally, finding irrational numbers, for example, the cube root of 2. Here we have to be a little bit more clever and come up with a function whose solution, or whose 0, is at the number we're interested in. So here we have f of x equal x cubed minus 2. And let me just show you where this function f of x came from. We're interested in finding an x value that's equal to 2 to the 1/3. And what we need out of this is a function that's easy to evaluate and has a 0 in the right place. So we cube both sides and subtract 2 from both sides. And now we have a function, x cubed minus 2, that's equal to 0 whenever we're at the point of interest. Okay, so here's an example, a graph of this function. How does Newton's method work? Well, first we start off with an initial guess that doesn't have to be particularly good. And what we do is we find the tangent line to the function at that point. So first we figure out the value of the function, its slope, and figure out the equation of the line. And then we follow that down until we get to the intersection with the x-axis. And that becomes our new guess, x1. And x1 is a little bit better. You can see this one's further from the root that we're interested in. This one's a little closer, but it's still not great. So what we do is we do that again. And so when we do, we find a new tangent line, follow that tangent line down to the x-axis, and now we end up with x2, which is quite a bit closer to the 0 that we're interested in. And we can continue this if we want a better and better approximation. And you can see that if we did continue it, we would get extremely close with very few repetitions of this method. Okay, so how do we actually calculate the successive estimates? So first we had to find a tangent line, and then we wanted to find where that tangent line hit the x-axis. And so here's a clicker question for you to think about. Find the x-intercept, and we're going to name that xn plus 1. So here are 4 possible formulas for the xn plus 1, and you choose which one you think is correct. And I will pause, let you stop and do some calculations, and come back with the answer. Okay, so I trust that you've done some calculations and you found which one of these is the correct method or the correct formula for finding xn plus 1. And in fact, it is B. And we can see that because, so we had L, let me change the color on that. L of x is f of xn plus f prime of xn times x minus xn. And we want to set this equal to 0 because we're interested in this point right here. So when is the line at a 0 height? And we want to find the x value of that. So this x right here will be the x1. So, or xn plus 1, I should say. So I can actually put that in xn plus 1. And now we want to solve what is xn plus 1 if we know what xn is. Okay, so first thing we do is we subtract f of xn from both sides. So we have f prime of xn plus 1 minus xn is equal to minus f of xn. And I'm going to emphasize throughout here, we might never ask you on a midterm or a final exam to derive this formula, but if you're just memorizing the formula without understanding where it comes from, you're going to be susceptible to making small errors like getting the plus or minus sign incorrect or having the wrong thing in the numerator or the denominator. So here as we solve, you can see why there's a minus sign that appears in front of the f of xn, and now you can see why f prime of xn is going to end up in the denominator. Okay, so those cancel, and now I have xn plus 1 minus xn, so I'm going to add xn to both sides, so I get xn plus 1 is equal to xn minus f of xn, all divided by f prime of xn. Okay, so there's, if you realize how to derive this formula, even if you don't remember or can't replicate all the details of it, at least if you remember that you had to subtract off f of xn from both sides, that will remind you that this should be a minus sign, and that you divided by f prime, that means the f prime goes in the denominator rather than the numerator. So these are little things that will help you remember this formula later on. Okay, so another thing to notice about this is the units. So another way to verify, if you forget whether to put the f on top or the f on bottom, the units, let's say f has units of, let's say, distance, and x has units of time. So we're trying to find the time at which this object is at a 0 displacement, let's say. So when you look at the units, xn plus 1 has units of time, so this is time. Xn has units of time. F has units of distance. And f prime is a delta f over delta x, which is a distance divided by time. And so when I put distance divided by time down here, you can see that I flip this and the time goes to the top and the distances cancel, and I'm left with a time, time, and time. If you got the formula wrong, then you would have mismatched units. So for example, if you'd put the prime on the numerator and the not prime on the denominator, then you would have 1 over time, and that wouldn't make any sense. Okay, so going on. Let's say to estimate square root of 3, which function would you apply Newton's method to? So I'll give you a few seconds to think about that, come up with your answer. Okay, hopefully you've thought about it. So let's see. X squared minus 3 has a 0 at square root 3, so that seems to be fairly good. There's another feature about it that's good, and option C illustrates exactly why. So option C also has a 0 at the square root of 3, but in order to use Newton's method, we would have to know the value of the square root of 3 in order to do any calculations, because f of x is in the formula. So what that means is C, in theory, has a 0 where we want it, but it doesn't have a very useful formula because we're actually trying to calculate square root of 3, so obviously we can't use that value in our calculations. So that's why D is a better option. All right, and now estimating square root of 3 using Newton's method, and I want you to use an initial guess of x naught equal 2, which is clearly not the right answer, but it's not far from the right answer. So time for you to do some calculations. So if you finish this and have a bit of spare time, I suggest you not only estimate it using Newton's method, but try to use linear approximation, which will require that you use a different function and approach this in a slightly different way, but you should end up with another approximation. All right, so I'm going to assume you've done the work and you have an answer and you've chosen one of these options. Okay, so I didn't specify how many times you should iterate. So should you just find x1 or x2? Turns out option A here is the x1 value. So that's what you get when you plug in x0 equal 2 into the formula for x1. So x1 is equal to x0 minus f of x0 over f prime of x0. If you then do another step, so here you get a calculation and you end up with 7 over 4. And then x2 is x1, so you take this 7 over 4 and you plug it into the formula again, and you will get a new number that will require a little bit more complicated fraction manipulation, and there you'll get 97 over 56. Okay, so I won't go through the details, but basically with the first one you would have, let's go back here and make some space. So x0 is 2 minus, now f of 2, remember our f function, f of x is equal to x squared minus 3. So when I plug in 2, I get 2 squared minus 3 is 1. So I get 2 minus 1 over, and now f prime of x is equal to 2x. So if I plug in 2, I get 4. And there we have 2 minus 1 over 4. Oh, that is actually not so hard. There we go. I did calculate it, even though I said I wasn't going to. And now we can, do that over again, and if you did, you would find 97 over 56 is your next approximation. Now, you'll notice that this is a pretty good approximation to what's down here, which is the actual answer, at least to 13 or to 11 decimal points. And you'll notice with just 2 iterations, we're already getting down to web work quality accuracy for decimals. Okay, I will take a break here so that this video doesn't get too long, and in the next one, I will go over to Desmos and talk a little bit about how to choose or how not to choose x naught.